Okay, so first a caveat. Thomas Bagrel has thought about all of this much more than I did. So everything smart is his, everything dumb is mine. With that in mind, I want to talk about map. Takes a while, okay, it's fine. So map famously, the map on list, if you write it the natural way, is not tail recursive, and this is kind of bad. This is kind of bad because it consumes stack space, and this is limited and all that. And the usual solutions are something like the two functions on the right. I don't think you can read it very well. I chose my colors poorly. They look brilliant on my screen. I'm really sorry. So it's all fairly systematic. One way is to transform map by continuation. You take a continuation, everything becomes tail recursive. That's nice. Though you might notice the question mark at the bottom of the slides. It's not really a good sign usually. And another solution is to accumulate everything in reverse and reverse the list at the end, which is not really a different solution. It's just a defunctionalized version of the first one. It has the advantage of eliminating that all three functions do exactly the same thing. You switch stack space for heap space, but at the end of the day, this just means we go down the list and then we go up the list. This is a two-pass algorithm, and that's why it's kind of bad. And the real problem with that is that it shouldn't be, right? If we allow mutation, it's very easy to make a map that is tail recursive. You just keep a pair of a reference to the head of the list and a reference to the back of the list, and when you want to add an element to the list, you grow the back of the list by mutation. Here I wrote it in OCaml, so I had to change the type, but that's the way like a Java program would do it, right? But in a functional programming language, and at least a pure functional programming language, you won't be able to do that. You can't do that purely. This is mutation, and I'm jealous. And jealousy is good. Jealousy is, people do better things than me. Well, I can try to solve that problem. So that's where we're going. Also, it seems that, okay, my screen is broken, but it's fine. Okay, so one solution that exists today in OCaml, there's all OCaml code so far, by the way, but if you are into Haskell, there's a few Haskell slides at the end. Is to add this tail modulo const annotation on map, and the compiler magically compiles it to the Java version, kind of. Just imagine it does. And that's really, really nice, because I don't have to do anything. You write the map that you want to write, no problem, and it is efficient. But it's not very flexible, right? You need to fall into one of this pattern that the compiler recognizes. And that's quite a few, but there's plenty of more things you can do if you have actual programming tool. So to solve this particular conundrum, I want to go a little bit more back in time, actually, and talk about an observation that Minamide did. I didn't write the date on the slide, so I don't remember when it was, but in the 90s. The observation was, in the continuation passing version of map, you use the continuation in a very specific way. For one thing, the continuation is used linearly. And then there's another observation that it is used, I should probably just point it out directly, that it doesn't actually pattern match on L prime. You can read L prime? Yeah, you can. Okay, great. And with these two restrictions, it is possible to come up with a new type of functions. Here I wrote it linear arrow hat. So it's a restricted type of function that you will only use linearly because you're going to mutate it, so you don't want it to be the mutation to be observable, and that never pattern match or read does anything dangerous to L with its argument, because otherwise you would read unrestricted memory. But with these conditions in mind, I mean, they could take this function type or something that looks a lot like this and compile it to the Java version. That's great. So I guess this is the end of the story, but not really. There's much more things that we can do if you give us a little bit more fun. I forgot to mention in the previous slide that linear types are not necessarily necessary. Like Lorenzen and Lyon, who are specialists of saying linear types are not necessary, show how to do that with just reference counting and copy on write. That's more recent. So consider this problem. So I have a tree on the left. It's the tree of unit, so it doesn't matter what's in the nodes, but I'm going to label each node with its position in the breadth first traversal. So the root is 1, and then the two children of the root are 2, and then you have, there are 3 children, are 4, 5, and 6. Do you know how to do that in pure functional programming? It's not, like, it's not easy. Like, papers have been written about it. So it's not immediate how to write this algorithm purely. But on the topic of being jealous, you learn how to do that in imperative programming in your first year of algorithmic class. All of us know how to do that. You put references in a queue and you generate a tree in breadth first search. It's very easy. So, yeah, jealous again. So, the solution for that is to have some kind of restricted form of references. And the inspiration, again, like is linear logic. In linear logic, the function is decomposed into a par and a primitive, like a first-class input type, that alpha dual. It's an input of type alpha. And we want similarly to decompose Minamide's function into this quickly symbol that we call an ampar and a destination, which is a first-class whole. So before that, we had only context. We had a list with a whole. Now we have a value for a whole. And that gives us a lot. And so, yeah, it's the same decomposition. And that gives us a lot. And the truth is that we can actually do a breadth first traversal with a normal algorithm. Like, you have a queue, you put things in a queue, the queue is functional, but we know how to make functional queues. Like, you take do lists or something like that. In the paper, we even use destinations to make the queue, so it's a lot more fun. But that's a discussion for another day. The point is, now it's really easy. Like, if I give you the tool, I give you the API, you'll find how to do that in 15 minutes. And you have like, you have similar restriction on this ampar type than you had on the hat function, right? You can't read the output, the inputs in an unrestricted fashion. But then, like, this is very easy to set up. But not everything is easy to set up. And the point is, linear types don't matter. Don't matter. Of course they matter. They don't suffice. Linear types don't suffice because destinations can break the linear contract. If I take a linear function like that, this is a function, a non-linear function, it just uses its argument alpha of type alpha only once. But it captures a destination. And during this function, I fill the destination with the argument, and the argument will escape. And the contract of linear functions that when I evaluate the result, I also evaluate the argument. That's a pretty lazy version to think about it, but you have the same story happens, right? The argument escapes instead of being part of the beta. And that is bad. That breaks basically every linear API out there. This is what you rely on, you break it. And in particular, that would break destination. If I can put a destination in a destination in an unrestricted fashion, then I can read an uninitialized memory. So the solution that we had to come up with was a new type system. So it's an extension of a linear Haskell. Linear Haskell is basically the stuff on the left. Like, it doesn't really look like a type system, but it really is secretly. Because linear Haskell is a type system in a tradition that was first proposed by Geeka in, I think, 2014, where the whole type system is parameterized by a summiring of modes. And modes with linear Haskell are just, am I linear or not? And we have to add, in addition, like numbers that represent scope, that represent, am I capturing a destination that I shouldn't? And so let's just put restriction on what we put in destination to avoid linear values escaping their scope. So this is a bit related, very, very vaguely, to Rust's lifetimes. But so every time we enter one of these AMPA, we increment the scopes and we just count how old things are so that we can use them in the right order. And there's a whole bunch of restrictions on destination to make this work. Okay. And infinity is an age for things that are normal values and they don't care. So these are really ordered summiring. You have the order on the top. And the fact that you have two summirings, the product of summiring is a summiring, and the type system almost works by itself. So I'm going to stop here. Here are a few links. Follow our blog. You will find more on this in the coming weeks, hopefully. Slides. The QR code is a link to the slide. And questions.
Thank you. So this time you can take as many questions as you want, almost. So if you have a question, please go to the mic.
Do you have a slide with the actual code of the breadth first search traversal? Because I have trouble picturing.
No, but it's in the paper. You can look it up.
Definitely read the paper.
I have some slides with code, but not this one. Mm-hmm. Sorry.
Okay. And so, have you considered implementing it in Haskell or Camel or something else?
Right. So the problem is the H system is an express type system, so you have to somehow fit it in, and you don't really have that luxury, Camel or Haskell. So what you have to do instead is finding appropriate restrictions of the general type system that will work for Haskell. But there is an implementation where the restriction is, well, you can only put unrestricted nonlinear things in destinations. That solves the problem because you can't break linear things anymore, but it's very restrictive. It's useful for some use cases. And there's the Haskell implementation. There's a GAC proposal to implement the compact region API that way. But there's and to go further than that, there are thoughts, Thomas has thought about that and designed some APIs, but it's very prospective, and so it's never really followed up with a real implementation.
So you think that the future functional programming languages should have this system, the general system, right?
I hope so. I don't know, maybe.
Okay, are we done with the questions? So let's take the speaker again.